I don't know if this angle is good or not. There we go. We are going to be looking at MacLauren's and Taylor's series. Essentially, we're going to look at how do you find power series, MacLauren's ones. Remember, MacLauren's is centered at 0, so they always x the ends. So let's look at those first. This is the formula. Any well-behaved function, f of x, can be written as MacLauren series. And so f of x will be written as a series from n equals 0 to infinity. The nth derivative evaluated at 0, x to the n over n factorial. Now, when we say well-behaved, what are we talking about? Well, the function should be differentiable, should be continuous. You know, it shouldn't have vertical asymptotes anywhere near the center. Should certainly not have any weird, you know, piecewise things going on, right? Just basically a nice smooth curve, right? With nothing particularly unusual happening. That's what well-behaved looks like. There are some functions where we know the entire series. In other words, we have a formula. I'll give you an example of one. Let's find the power series for e to the x. Well, you find the first derivative, you find the second derivative. You might even find the third. You find as many derivatives as you need. Now, e to the x is so easy to differentiate, you could keep doing it forever. You then find the value of the function at 0 and all the derivatives at 0. In this case, it's e to the 0, e to the 0, e to the 0, e to the 0. Can you see that's a very simple situation? What you then have to do is you have to find a formula for the nth derivative at 0. Would you agree that for e to the x, that answer is going to be trivial, isn't it? Just 1. Are we good? So, if you want to find the power series for e to the x, it's going to be the series from n equals 0 to infinity, the nth derivative at 0, x to the n over n factorial. We have a formula for the nth derivative at 0. It just ends up being 1. And so the power series for e to the x is that guy. Wasn't that the guy we played about with the... I can't remember if we did that on Thursday or I showed you my little video on Friday, but you remember doing that guy? E to the x. The more terms you do, doesn't it look more and more like e to the x?
I'm awake.
You're not.
And I am going to talk quite a lot right now, because we do not want to hear other people's private conversations that I think I successfully talked over. Right, so where are we? Here we go. So we're comfortable with that one? Do you know that it's very difficult to actually create entire power series, right? Can you imagine that these derivatives evaluated at 0 might not have an obvious pattern or even have any pattern that you could see? So that's pretty rare that you get that. But there are some examples of that happening. So that's e to the x. Right. I'm going to do a function, the natural log of 1 plus x. And let's see if we can find the power series, the MacLauren's power series for that guy. So if you evaluate this function at 0, you get the log of 1, and the log of 1 happens to be 0. Okay. If you find the first derivative, you get that, and the first derivative at 0 is 1. if you do the second derivative, you probably want to call this guy 1 plus x to negative 1 now. So if you do the second derivative, you get negative 1 plus x to negative 2. If you get the third derivative, you get positive 2, 1 plus x to negative 3. If you do the fourth derivative, you get, well, I really should be writing this a little bit differently. You get negative 1 times 2 times 3. I was about to write 6, but I've changed my mind. I'm going to write it that way. And one last one. If you do the fifth derivative, it's going to be positive 1 times 2 times 3 times 4, 1 plus x to the negative 5. And theoretically, couldn't I keep going? Right, so I found the first up to the fifth derivative. Now we're going to put a little line there. The second derivative at 0 ends up being negative 1. The third derivative at 0 ends up being positive 1 times 2. The fourth derivative at 0 ends up being negative 1 times 2 times 3. And lastly, the fifth derivative at 0 ends up being positive 1 times 2 times 3 times 4. So I need to know what the nth derivative is. Right, forget about that one there. That one we basically can ignore because we'll just start our series at 1. Right. So the first derivative, second derivative, third derivative, fourth derivative, fifth derivative. I need the nth derivative. I'm chucking you right in the deep end, understand that. But has anybody got even a piece of the answer? I don't need the whole answer, but do you see any pattern going on here?
Would it start with a negative 1 to the power of n? Trying to make sure I get the negatives right.
Okay, so the first derivative gets you 1. The second derivative gets you negative 1. If you made it n, the first derivative would be negative 1. So how about n plus 1 then? That'll fix it. But noticing it alternated. You know, when it's alternating, it's always negative 1 to the n or negative 1 to the, n plus 1. Now, you notice how I didn't turn these into numbers, but I left them as calculations. And I did that so that you can hopefully see a pattern. Do you recognize that 1 times 2 times 3 times 4 is just another way of saying 4 factorial? And isn't 1 times 2 times 3 really just 3 factorial? And 1 times 2 is 2 factorial. And 1 is 1 factorial. And with a little bit of imagination, couldn't I call that 0 factorial? So what do you think the nth derivative is going to be?
N factorial?
Close.
N minus 1?
N minus 1. The fifth derivative is 4 factorial. So it's going to be n minus 1 factorial. Does that make sense? That the fifth derivative gets you 4 factorial. So we know this guy. And so we can now tell you that the power series, right, of this guy, this is f of x, is going to be sigma n equals somebody infinity, negative 1 to the n plus 1, n minus 1 factorial. And all we do is we start at 1, because remember that first term was 0. And so we don't really want to start at 0. And, oh, I forgot my x to the n over n factorial, because that's the derivative of the nth derivative at 0. That's this piece. There's the x to the n, and there's n factorial. Can this simplify? Can n minus 1 on the top simplify with an n factorial on the bottom? Yeah, they can. What do they cancel to then?
N-1 on the bottom?
Yeah. Oh,
Wouldn't it be n on the bottom?
yes, just n. Almost said it. But yeah. So there's our, you don't need brackets. There's our answer. That power series is this fella. And if you want to see it written out, you would get, well, when you plug in 1, you get a positive x, and then you get take away x squared over 2, then you add an x cubed over 3, then you take away an x to the 4 over 4, and then you add an x to the 5 over 5. Do you see that, guy? Yeah, that's what the power series looks like. Now, if I evaluate this at, say, x equals 1, which is a nice place to evaluate series, then the natural log of 1 plus 1, which is the natural log of 2, is equal to 1 take away a half plus a third, take away a quarter plus a fifth, forever. Do you recognize an alternating version of the harmonic series? And I hope I mentioned that, I think I did, that I knew that it added up to log 2. Can you see the reason I know it adds up to log natural log of 2 is because that's what its power series is at 1. So if you know the power series of a function, can't you evaluate that function at any given value of x by just replacing these x's by that number and then estimating the answer? Do you know that there are some functions out there that you haven't met yet, but hopefully a lot of you will? You know, you've met sine x and cosine x and e to the x, right? You've met functions like that. But there's some functions out there that you haven't met yet that are actually described by power series. There's a group of functions called the Bessel functions. And the Bessel functions are described as a power series. They just tell you what the power series for it is. Quite useful functions. If you ever get a chance to use them, they are used in the solution to advanced differential equations. So there are functions out there that only exist as power series. Are we good? Right, let's wind back now and do some simpler versions of this question. So we are not going to find a power series from scratch. Some nice person has found out that the nth derivative at 0 happens to be n plus 1 factorial. Wasn't that nice? And our job is to find out what the power series would look like in this question. So the general version of a power series, a MacLauren version at least, is that guy. And then we do style points. Would you agree this simplifies? Okay, what would this one simplify down to? Because that's the answer they want, the simplified version of the power series. So we have an n plus 1 factorial on the top, cancelling out an n factorial on the bottom. What's left?
N times x to the n.
Are you sure about n? You're close, but not quite there. Okay. N plus 1 factorial is 1 times 2 times 3 all the way up to n, and then times n plus 1. And the bottom's just got all the numbers up to n. So when they cancel out, what is left on the top? It's not n.
N plus 1.
N plus 1. If you want to see what that might look like, if you do n plus 1 factorial, you get 1 times 2 times 3, you get n, and then you get n plus 1. On the bottom, if you do n factorial, you also get 1 times 2 times 3, but you finish at n. You see all the cancelling happens, and that guy is left. So we can we can cancel out factorials by simply, this kind of process. They also go on and ask you to find R, but I'm not going to do that. You will. Won't you just use the usual ratio test on this power series? Now, a different kind of question would be not to find a complete power series, but just to find the first, say, 4 terms of a power series, right? I should call it MacLauren series. So let's pick an example of a function that we could do that to. Suppose I went and told you f of x is equal to x sine x. And I want to find the first 4 terms. And we would center it at 0. That's just their way of saying MacLauren's. So I would find the first derivative, and that would be as a product rule. And that would be, I'll put it here, that would be 1 times sine x plus x times cosine x. Then we would find second derivative. So that's my first term, right? That's my second term. This is going to be my third one. So what do I get? I get a cosine x plus another product rule, which is going to be 1 times cosine x minus x times sine x. That looks like it's going to be 2 cosine x's minus x sine x. And that's my second derivative. That would be my third term. And then I'd find one more derivative and it'd be finished. So that would be -2 sine x. Ooh, a bit messy, but product rule, -1 times sine x minus x times cosine x. And that looks like -3 sine x, take away an x, cosine x. Now, if you're going to evaluate the first 4 terms of this series, here we are. I need to find this guy at 0, this guy at 0, and so on. So f of 0 ends up being nothing times sine nothing. F dashed of 0 ends up being nothing. I should have picked a better choice here. The second derivative at 0 is 2 take away nothing. And the third derivative at 0 is just 0. What a horrible question. But the answer would be 0, 0, 2, and 0. Right. Now, what would the first few terms look like? Nothing, nothing. That's first, second, that's 0, first 2, x squared over 2 factorial, and then nothing. And then that would be 0, 0, x squared, and 0. So there's the first 4 terms. 3 of them were just zeros. And that's because I picked a really ugly function to do it, which is why you should only pick homework questions, because they're designed to be nice. So I'm going to do this again, but with a much nicer function. Okay, there's my first term. That's still 0, so you do get zeros. If you do a product rule on this, you get 2 times e to the x plus this guy. And if you evaluate the derivative at 0, you get 2. If you find the second derivative of this guy, you get this fella plus this fella plus that one. And that simplifies. Yeah, this is much nicer. And the second derivative at 0 ends up being 4. I'll just do one more. So if you want the third derivative, you get this guy, product rule. So the third derivative at 0 ends up being one of these is an x in it. That one. There we go. You get 6. So the power series so what do we get? If you plug in 0, you get the first one. So you get nothing times x to the 0 over 0 factorial. The next term you get is 2 times x to the 1 over 1 factorial. Then you get 4 x squared over 2 factorial plus 6 x cubed over 3 factorial. That guy gets you nothing. That guy gets you 2. That guy gets you 2. Interesting. That guy gets you 1. If I continue this forever, wouldn't this be the power series for 2x e to the x? And I would have hoped that WebAssign just wanted you to write that, but evidently WebAssign, in its infinite stupidity, wants you to write that. So if a term is 0, it doesn't get written down. I think that's a much nicer way of writing it, but evidently that's what they want. So you'll see comma separated list. That's what they're talking about. Don't write the zeros down, just write the things that aren't 0. And if it's 3 or 4 of them, that's how many you need to write down. Are we cool with that one? God, the time shoots by. This guy is that function. We are going to take this fella and we are going to do first 4 non-zero terms. Oh God. Right. If you differentiate, well, let's get this thing. Evaluated at 0, the answer is 2, so that's good. If you differentiate this guy, shouldn't you think of them as 2 cosine x's being squared? So this is essentially a chain rule. So it's going to be 4 times cosine x times the derivative of cosine x, which is negative sine x. Are we good so far? If you differentiate 2 cos squareds, you get 4 cosine x's times the derivative of a cosine x. Now I'm going to do something here that's going to make my life and your life a lot easier. We're going to do style points. Somewhere in 142, you saw an identity that told you a multiple of sine x cosine x was equal to somebody. Can you remember that formula from a way back in the day? some multiple of sine x cosine x equals somebody. Okay, it'll be even nicer. 2 sine x cosine x is equal to somebody. Who is 2 sine x cosine x equal to?
Sine of 2x.
Correct. So 2 sine x cosine x can be replaced by the sine of 2x. Now you're going to look at that and say, that guy is not this guy, but he is pretty close to this guy. What could I rewrite this in terms of sine 2x? What multiple would it be?
-2 times sine of 2x.
Now you might say, why am I going to all this trouble? Well, aren't we going to be differentiating for a lot? Wouldn't it be easier to differentiate a sine of 2x than the sine of a product? Would you agree that it just gets uglier and uglier as you go on? So now that I've got this guy, I can find his derivative at 0. Unfortunately, it happens to be 0. But the second derivative can be done through a chain rule. So it's -2 times 2, which is -4, cosine of 2x. That's easy to do. The second derivative at 0 then is -4. The third derivative is going to be -8 times a negative, so it's +8, the sine of 2x. And the third derivative at 0 equals 0, so I can't count you. I'm not doing too good here. I've got one answer. I've got 2 answers. If I do the third derivative, I get 16 cosine of 2x. And the fourth derivative at 0 ends up being 16. How many do I need? I go and do the fifth derivative, which is -32, the sine of 2x, but the fifth derivative at 0 is 0, so I don't want to use it. And then I get the sixth derivative, and it ends up being negative, I believe, 64, cosine of 2x, and that sixth derivative at 0 happens to be -64. So I did finally get 4 non-zero terms. So far, so good. They don't want us to write those guys down, but they do want us to write down what it would look like with all its powers and things added on. So if you write down MacLauren series in its expanded form, in other words, you just write down the terms. It looks like this guy. Can you imagine that continuing forever? So I'm not writing it as a series, I'm just writing the series down in this format. So that guy is a 2, this guy is a 0. This next one is -4, so that's -4 x squared over 2 factorial. The next one's a 0. This fella here is 16 x to the 4 over 4 factorial, then a 0. And then I get -64 x to the 6 over 6 factorial. So I've got 2. This guy and this guy cancel, and you get that. 4 factorial is 16 over 12. 16 over 12, where would that go? That would get me 4/3. And this last one, 64 over 6 factorial is getting to the point where I don't want to risk my brain. So I know the answer is negative, so it's -64. -64 divided by 6 math, move over to there and get the factorial guy. There's the answer. Hit the math button, turn me into a fraction, and -4/45. Would you agree it's much easier if you just let the calculator handle the ugly ones? And that answer would be the way I would expect to write it. But WebAssign wants you to write it as 2, comma, negative 2x squared, comma, 4/3 x to the 4, comma, and negative 4 over 45 x to the 6. Can you kind of understand what they want you to do then when they say the first 4 non-zero terms of a MacLauren series? You're going to have to do lots and lots of derivatives. Hopefully not too many, but certainly, a good chance there will be. And the ones that aren't zeros, you'll then write this guy down, plug him in, put in the zeros to make sure you get the powers in the right place, and then get this guy, and then finally this guy. So far, so good. I'm going to try a couple of these just to get a feel for them. So if you bear with me for a few seconds. I'm going to go hunting for Desmos. And we're going to put in the original function. And then we'll put in what the MacLauren series looks like for that same function. And we'll see how good a match it is. And because it's a MacLauren series, I know it's going to be best at 0. And then as x travels away from 0, it gets less and less, what's the word I'm looking for? Accurate. Yeah, that's a good word. Right, almost there. Got it. Right, now, see which ones we have. So I'm going to do 2x e to the x. So in here, y equals 2x e to the power of x. That was the original function. Got an interesting kind of curvature to it. And the guy that we had was y equals 2x plus 2x squared and plus an x cubed. Now, if I kind of move this around a little bit and kind of focus in, would you agree actually it's a really good fit on the right hand side, isn't it? Not such a good fit in the left. But can you see that power series, which is this cubic, is pretty close to being the same shape as 2x e to the x. And that's only what, with 3 terms? You can imagine I did 10. I mean, let's do this. If I zoom in here, can you see how close the red and blue are to being the same fella? I mean, that's pretty amazing how accurate that is. But one of the properties of MacLauren's and Taylor's series is that it's the first 4 or 5 terms where all the information is, right? Once you put in plus 4 or 5, you're pretty good at 0 and close to 0, right? Obviously, I wouldn't use it when x is 100 because by that time they would have drifted, but they're pretty good. And the other one we did was 2 cos x squared. So let's see what that one looks like. 2. I'm thinking the best way to do this, I should be able to do cosine x, finish a bracket, and do a square. Okay. That's 2 cosine x squared. And then for my second function, we have 2, take away 2x squared, plus 4/3 x to the 4. And then finishing with negative 4/45 x to the power of 6. Would you agree it's a pretty good fit near to 0? Shrink it back a little bit. There. In that range there, would you agree it's a pretty good fit? And would you agree it's pretty horrible over here? But close to 0. So close to 0 would be, right, maybe a little bit closer. Yeah. Would you agree in this range it's pretty good? That is amazing. every function in the world is really a power series, or can be represented by a power series.
Would the region that's matching be like the interval of convergence?
Well, the interval of convergence is connected to that. In other words, if the interval of convergence was -1 to 1, you really only can be sure that in that range it's going to do a good job. If you don't choose one term, would you get me? I mean, if you pick one term, isn't it going to be horrible? But if you pick 8 terms between -1 and 1, it's going to be pretty darn close. So they're not exactly the same, but they are very similar, right? Pretty cool. So where are we off to next? Let's close that window off and get back to our original. Change the subject just for a little bit. See the math that you're doing right now, and hopefully are fairly comfortable with what we've done. If you could have went back 400 years ago, right? We didn't know this stuff. Really, the mathematics of those days wasn't really influenced by algebra. Algebra wasn't actually even written the way, you know how you write x squared plus 4x? Even that hadn't really been created yet. If you look at old manuscripts, because sometimes I do photocopies of them, they don't say x squared plus 5x plus 1. They say an unknown quantity is squared plus 4 times that unknown quantity plus 5 was equal to 0. Right? It was very English sounding. It's like somebody was writing something down. Can you imagine how difficult it was when you did math that way? And can you see the elegance of algebra? Of how it allows you. I wouldn't even think about that. So anyway, if you went back to time, you would be considered the best mathematician in the world. Because you knew something that they didn't. And if you were really sneaky about it, wouldn't you never tell people what you were doing? You would only produce the results at the other end. So there was a lot of knowledge that was probably knew by the ancients, right? Ancient mathematicians, but the buggers kept it secret, and then they go on and died, and nobody knew what it was. Right? Can you imagine Pythagoras' theorem if he just kept it to himself? Couldn't he come up with all sorts of answers to triangles and areas of things, and people didn't know, how the heck did you figure that out? And he would just say, I'm clever. And then he goes and croaks. And now nobody knows Pythagoras' theorem anymore, right? The knowledge disappeared. So I'm not saying that the ancient people were dumber than we are, because they weren't, but they're not as, they didn't know as much as us is not the same thing as being dumber. And one more thing, because my brain is on it, and then we can get back to this. MacLauren didn't know what to do until Newton had created calculus, right? If you didn't know what derivatives were, you couldn't have created this, right? You needed to know something that someone else found for you. And that's how science worked, right? Somebody discovers something, then people check it out to make sure it's true and that it works. And once that's kind of accepted, people build on that and make other things from it. Well, he did that. Sir Isaac Newton is, in Britain at least, and probably in America, is the one that we said created calculus. If you're a German,
credit to Leibniz? No Leibniz?
Exactly. No
I love
Leibniz.
Leibniz.
Leibniz was a thief and a cheat, allegedly, according to Newton, because Newton discovered calculus, and he was doing the clever thing that they did in those days. He didn't tell anybody. And he was using his calculus to prove things. But once he proved them, he used classical mathematics when he published his papers. So the calculus did it really quickly because he knew what the answer was going to be. And then he used classical math to prove that thing. And he sent a letter to Leibniz and said, hey, Leibniz, look at this cool thing. And Leibniz published a paper basically copying, allegedly, what Newton had told him. And Newton was, to coin a phrase, pissed off. And it caused a lot of problems because the normal scientific world understands a simple rule. The person who figured it out first gets the credit. So if you publish something, you publish it, but you say, this is not my work. This is Sir Isaac Newton's work. I'm just publishing it because it's cool, right? But that's not what Leibniz did. Now, allegedly, and it could be true, Leibniz, in his defense, said, I got that letter from Newton telling me all about this cool stuff. But guess what? I'd already figured it out and I wasn't telling anybody either. But once Newton sent me that letter, I thought, I better publish my idea before he does so I can get the credit for it. So you believe who you want. It's not like a German ever did anything bad, right?
It sounds like they both shot themselves in the foot just a little bit.
Right. But the history of math is kind of interesting. Okay. Now, goodness gracious me, that's what I get for blethering. What are we going to do here? We are going to do a function from start to finish again. And I'm going to cheat by telling you a lot of the answers, right? So we are going to do an entire power series for that function. And I'm just going to tell you what all the derivatives are and see if you can discover a pattern. So you just have to imagine that I found the first derivative, the second derivative, and all the other guys. And the pattern, I've got it in front of me here, so I don't need to do it either, was 0, 5, negative 25, confused, 250, and finally, negative 3, 750. Wow. Let me call this guy 125, which is 5 cubed times 2. Let me call this guy negative 1 times 25. Let me call this 1 times 5. Yeah, that's going to work much better. And let's do the next one. Is going to be, what would the next one be? 125. There. Can anybody figure out what the pattern is to get the nth derivative? And can we forget this guy because he's 0 and he doesn't have it? And I'm going to tell you there's 3 pieces to it. Let's do the plus minus one. Plus minus plus minus. Doesn't that get generated by negative 1 to the something? So the first derivative is positive, the second is negative, the third is positive, and the fourth is negative. What does that look like? How would you generate this combination of pluses and minuses?
In -1?
Did you say n minus 1?
Yes.
Yeah, and totally cool with that. It's correct. And write it down. I'm just going to put n plus 1. Why? Because I only use 2 answers, n and n plus 1. Right. The n minus 1 is totally correct. Now, I said there's 2 things. 5, 25, 125, and 625. The first is 5. The second is 25. The third is 125. The fourth is 625. Any idea how you get the nth one?
Is it 5 to the nth power?
You nailed it. Now, you don't get a lot of experience with factorials, right? But once you've seen them enough, you start recognizing them. That guy is going to be 0 factorial. This guy, just the number bit, is 1 factorial. This guy is 2 factorial. And this guy here is 3 factorial. The next number, by the way, would have been 24, and that's 4 factorial. So you'll get used to seeing 1, 1, 2, 6, 24, 120. The minute you see that combination, it's factorial world. Okay, how many factorials for here?
It would be n minus 1 factorial.
You have now created that fella. So don't you just stick this guy, and this guy, that's the nth derivative, x to the n over n factorial, and you just start at 1, right? Because you've missed the first term. And we've seen this happen once before, at least. Won't the n minus 1 factorial cancel out the n factorial? And when it does so, you will be left with just a single n. And there is the power series for the natural log of 1 plus 5x. So you now know how to calculate the natural log of 1 plus 5x for any value of x you like, but keep close to 0. In fact, I believe this one has a radius of convergence of, oh, don't quote me because there's 2 answers, either 5 or a fifth. I can't remember which. So from minus a fifth to plus a fifth, it's great. Or from minus 5 to plus 5, it's great, right? The radius of convergence. So you have just done what Newton did, or what that thief Leibniz did, depending on your European ancestry. Do you know which side the French went? All of the Europe went with Leibniz. Except Britain, we went with Newton. To finish with a quote, so one person allegedly said to Newton, what's it like to know all these cool things, right? These really great things that no one else had thought of. And he was quite modest in this answer, because typically he wasn't. He said, the reason I can see so far is that I'm standing on the shoulders of giants. And what he was trying to say here is, I didn't create all of this. I only added to the knowledge. Other people who came before me, figured out algebra for me, right? And figured out, expressions and all the other things that he needed before he could make calculus happen. So I thought that was quite modest of him. I think Leibniz just said, let's invade Europe. No, that was a different German. I forgot. Right. Okay, have a nice day, everybody. Make sure you say your last name, and I'll hang about for questions.
I have a quick question from one of the homework sets.
Sure.
So it is from the 11.9 power series of functions.
Okay, give me a second. I'll look it up.
Thank you.
Aren't power series cool, Kira?
Oh, they're so cool. I love them.
Yeah.
I didn't think I was going to love them, and now I do. So.
Right. Accidentally, I've got a window in the way of my other window, so I'm having problems. So if you can bear with me a little bit more. Is it there? Yeah, there it is. Right. So 11.9 power series, you said?
Yes. Question 9, part B.
Question 9, part B. Let me find yours. That way the questions will be the same.
Okay, I think it'll be pretty standardized because it's just asking an f of x equals e to the x, like there's no specific numbers in it.
Okay, good. So I don't need to do that after all then. Number 9?
Yes.
Okay, almost there. Oh, second last question. Okay, so It then asks you to find f dashed of x. Is that the one?
Yes. Yeah,
Okay,
basically.
so where was it going weird for you?
So
What were you having
basically, on the part B, the part that got me mixed up is that they took this dy over dx equals y, and then they switched it around so it's dy over y equals dx, and then they said integrate both sides, and
Okay.
my brain just couldn't put together what they were trying to accomplish. I was like, is it 1 over e to the x? Is it integral? Like,
Gotcha. Okay. They're using can you remember the end of Calc 2? And at the end of Calc 2, we did solving differential equations. Remember?
Mhm.
Did I get you? Yes, I did, didn't I?
Yeah.
Okay, good. So I know that we've covered that then, just in case you got someone else who may not have covered that. Okay, so I'm trying to get back to my first window so I can see sure what I'm doing right. So you had this, right?
Mhm.
Now, this is not variable separable the way it's written. Now it's variable separable. So the integral of 1 over y dy is equal to the integral of x dx. So far, so good?
Okay, yeah.
Now, the integral of this is the natural log of y. Don't need that. And the integral of this is just 1. Gets you x plus a c. So natural log of y is the integral of 1 plus an average of constant c. Now, if you take both sides to the power of e, you get y is e to the power of x plus c.
Okay.
And then they're going to do this little sneaky thing. It's e to the c times e to the x.
Mm-hmm.
And then you say c is an arbitrary unknown constant number. E to the c is just an equally arbitrary constant unknown number. So why don't we just call it c?
Mm-hmm.
And you've got this. Now, you know the function at 0 is 1. Right, somewhere or other, I'm trying to find out where they told you it. Yeah, since the function f of x, that's kind of redundant. But you know f of 0 is 1. So y at 0 is c times e to the 0. So y of 0 is c. So that makes c equals 1.
Okay. That
And-
I kept trying to plug in the y equals e to the x part, and that's what I think was messing me up.
Right.
Because I didn't just leave it as y until the end.
So you have got two boxes. You've got this box here, right?
Mm-hmm.
And that's what's going to go in. That's like almost at the bottom. And then they have another box where f of 0 equals, and you're meant to put 1 in it, and that's what the other box is.
And the other one's 1. Okay, that makes more sense now.
Okay.
Awesome,
Any
thank
other?
you.
You're welcome. Any other questions? Are we good?
Yeah, I have a
Uh,
question. Or yeah, go ahead.
Right. No, Dylan,
Dylan,
whatever.
I'll take it. It basically was just on the last question you did. I didn't get how the fourth one you did, you got -6 times 625.
Yes, this one.
Yeah, how'd you get that from 375?
Oh, because it's not. There's a 0 missing.
Okay, well, yeah, I don't have a question anymore then. Thank you.
Okay. Right. Next, Alec.
for the homework question, did number 3, where you listed 2 negative 2x squared.
Is that the one we just finished doing a minute ago? Or at
Yeah.
the beginning of today? Right, let me
It
find
wasn't. Yeah, it's
notes.
number 3 on the homework.
Okay. I know I've got all sorts of notes mixed up here. Okay, that's my stats notes. We don't need them. So it must be down here somewhere. Is it this one?
No.
No.
It started out with 2 cosine
Yeah,
squared.
that one. Yeah, got it.
Yes. I had the exact same question in for the homework, and when I inputted the answer, the way you written it, it didn't work.
Okay, what question number is that again, so I can look at their answers? Is it,
3.
3. It might be me just screwing up with the, right, 163. MacLauren series. Most likely mistake would be me getting my signs wrong or something. So I got 2, 0, -4, 0, 16, 0, -64. Okay, so I can tell you that that is correct because it matches them. And I have 2, check. -2x², check. Oh, there we go. This one here is 2. So I simplified this one. So it's 2/3. And the last one I got right. So I said that was 4/3 and it was only 2/3. So let's check that out. If you take 16 and you divide it by 3 factorial, that's 16 divided by 6. Is that 3 factorial? What one was that? Fourth
I think
derivative.
it's 4.
4 factorial. Okay, so that's 16 over 24. And divide the top and bottom by 8. There you go, it is 2/3. So it was just an arithmetic mistake that this guy was actually 2/3 and now it's correct.
Okay. Another question I had was for the midterm that's happening Monday next week, right?
Correct, and it's going to happen in your case, everyone's case, it's going to be happening in a 2-hour window. So
Okay.
it's going to start at 8 till 10 or 9 till 11, depending on which one of those 2 windows works best for you. If that doesn't work, then you need to tell me and we'll figure out something else.
Okay, I was wondering if it was like an hour test or like a 3-hour test, like a final.
It's going to be a 2. The final will be 3.
Okay.
So which one of those 2 is going to suit your schedule, the 8 to 10 or the 9 to 11?
Oh, the 8 to 10 will be fine. I was just wondering how it was going to go down.
Okay, then hopefully I've answered that. Right, Maggie, you got a question or are we good for right now?
I do have a question.
Cool, what you got?
So for the last problem we did, for the final form of the answer, you wrote the summation of n equals 1 to infinity of -1 and n plus 1, 5 to the n, x to the n. Is that the final form, or would we be required to combine the x and the 5?
Leave it alone. The style rules for series is x's should be on their own. So
Okay.
you would actually, in no situation I can think of, would you do that. In fact, if you do a different question and it ends up being, that kind of thing, you're expected to separate it always. So that's the convention. X to the n must be left separated. Oh, it's a nice, easy question.
Yeah, thank you. So my other question is about the first one we did. I wasn't writing quick enough to keep up with you.
Go on.
No, it was, you did question number 1, I guess.
Okay, I forgot what one looks like, so let me find it so I can get it. Oh, they gave you the formula, which was really nice of them because that's where all the hard stuff is. Now I have to find it.
It's, oh, wait. It might be on the same page, but it's
Yes.
f of x equals x sine x. That one.
Oh, that one. Yeah, that was a horrible question. I made that one up. The reason why it was a horrible question is that a lot of the numbers ended up being 0. And that, there we go. Here is the first 4 terms. only one of them actually came out as not being 0. So if you had to do this question and you had to do the first 4 non-zero terms, can you imagine you'd have to do maybe 20th derivative just to find 4 of them that weren't 0? So bad choice of question.
Okay. What
The
are the
process is correct, but that doesn't help. Yes.
braces? What are they representing?
In the homework, they want you to write it as a comma separated list. So when you have a comma separated list, you don't have the little curly brackets. I do. You just write down. Well, actually, you won't even write that down because they almost always want you to write down the first 4 non-zero terms. So you write that one down, and let's just pretend, because I don't know the answers, that that's the second one. That's the next one, and that was the one after that. So you just write them down as a list with little commas beside them. And it's called a comma separated list. But the little curly brackets you don't need. I do that because it's set notation. And I can't help myself. I always put curly brackets around things that are lists.
Okay. So I guess I'm just confused where the values came from. I understand the first line, but then the second two.
Where did this come from?
Yeah, the second two comma separated lists. I'm not understanding where their values came from.
Is it this list here you're talking about?
Yeah, and the one above it.
Okay, so if you write down this fellow over here, right? See this guy here? If you write down a particular one, so there's the only one that came out as a number. See that guy is 2 on the second derivative? So on the second derivative, the term that you would be using would be the second derivative at 0. Do it again. The second derivative at 0, x squared over 2 factorial. That would be the term that you would get from the second derivative. Now that happens to be the number 2. That's an x squared. And this is 2 factorial. 2 factorial is the number 2. They cancel out, and that's where the x squared came from.
Okay.
Right, can we pretend a different story that the 10th derivative at 0, that's a bad choice, that's a huge number. The 10th derivative at 4, right, happened to be 20, right, just for argument's sake. Then we would have the 4th derivative at 0, x to the 4 over 4 factorial. That would be 20 x to the 4. 4 factorial is 1 times 2 times 3 times 4, so that's 24. And then I would cancel them down and get 5, 6 x to the 4. So that would be the term that you would get from the 4th derivative. And this is the term you got from the second derivative. So you would continue to do this process until you found 4 answers that weren't zeros. Because there's a good chance that there are going to be some derivatives, you know, like the 3rd derivative at 0 is 0 and the 4th derivative at 0 is 0. So those ones you basically ignore and only write down the answers are non-zero terms.